we've been talking about different concentration units. And you might be wondering, why do we have all these different concentration units? Why can't they just use one so we don't have to learn all these different things? Different concentration units are useful in different situations. Chemists use molarity a lot because we're very concerned with the moles of stuff because we're looking at what the chemical reactions are. In other fields like medicine or water safety, they're interested more in just how much is in there, how much what can we use to measure it conveniently, and so that's why we see all these different units. So unfortunately, you have to learn them. A lot of it comes down to critical thinking, problem solving, and dimensional analysis. So let's do this one. A water sample is found to contain the pollutant chlorobenzene with a concentration of 15 ppb by mass. What volume of this water contains 5 times 10 to the 2 milligrams of chlorobenzene? Assume a density of 1 gram per liter. So we'll just follow the pattern we've been doing, and we'll highlight numbers that were given. And then we'll highlight what we want to find. So we want the volume of this water. So then let's take these numbers and write them down. So 15 ppb. Just looking at ppb is not going to be very helpful in trying to do this calculation. So we need to think about, well, what does that mean? ppb literally stands for parts per billion. And it's by mass, so that means the unit on the numerator and the denominator is going to be a mass unit. It actually doesn't matter what mass unit it is as long as it's the same on the top and the bottom. So 15 parts per billion means 15 parts, let's just say grams. So that's 15 parts, 15 grams of chlorobenzene per billion. That's 10 to the 9. There's no room for the 10 in there. 10 to the 9 grams of water. So that's what parts per billion means. And then I have another number, 5 times 10 to the 2 milligrams. Of chlorobenzene. And there's nothing fancy about that unit, it's just a mass. And then I have 1.00 grams per milliliter. And that's the density of the water. So that's 1 gram of water per 1 milliliter of water. So that's the information that was given. And then what I'm trying to find is the volume of water. And it doesn't say what unit I'm supposed to use. So what unit do you want to use? Don't say gallons. Should we do milliliters or liters? Milliliters? Let's do milliliters. So we're looking for milliliters of water. And then what we have to ask ourselves is, well, which of these things am I supposed to start with? Which one doesn't look like a conversion factor? This one, right? That can't be used to convert anything. That's just a mass of chlorobenzene. So that's what we're going to start with. So I'm just going to move these things around. because I can. It's kind of fun. So this is where we're starting, and that's where we're trying to get. So then these are going to be used in this calculation somewhere, right? So here we've got milligrams of chlorobenzene. Here we've got grams of chlorobenzene related to grams of water. And here we have grams of water to milliliters of water. So one of these is either the beginning or the starting unit. The beginning or the ending unit. Beginning and starting, it's the same thing. Here's milliliters of water. This one actually has milliliters of water in it, right? And so this would allow us to convert from grams of water to milliliters of water. So that could be the last step. And then this is grams of chlorobenzene to grams of water. But here I've got milligrams. Can I go milligrams to grams? Yes. So I can go from milligrams of chlorobenzene to grams. I'm going to start calling him CB because I'm tired of writing it out. And then to grams of water. Any questions about that? So now I'm just going to write out my calculation here, 5.00 times 10 to the 2 milligrams of CB. And then I'm going to go to grams of CB, and I want to divide by milligrams of CB, chlorobenzene. And then the next one is grams of water. And I need grams of chlorobenzene in the denominator to cancel out. And I'm going to go to milliliters of water. Milliliters of water. And I'm going to have grams of water down here to cancel it out. You see how the units work? Then I'm going to take the numbers from my other information here. 15 grams of chlorobenzene per 10 to the 9 grams of water. So that's this one in the middle, grams of water to grams of chlorobenzene. So there's 15 grams of chlorobenzene in 1 billion grams of water. And at the end, I have a density of 1. So 1.00 grams of water per 1 milliliter of water. And then the second one is where I'm using my metric prefixes to convert, right? So we memorized these at the beginning of the semester. We're going to still assume that you know them. Milli stands for 10 to the minus 3. So 1 milligram is 1 times 10 to the minus 3 grams. There's my calculator. Wow. I came up with this ridiculously small number. I'm like, what the heck? Because I multiplied by 1 times 10 to the negative 33. That's not good. Okay, that's better. I'm getting a heck of a lot of 3s here. 1, 2, 3, 4, 5, 6, 7, 8. I'm getting 3.33 times 10 to the 8th milliliters. And I'm thinking they're probably going to put that in liters instead of milliliters because it's just so big, right? So 3.38 times 10 to the 8th milliliters. I can convert that to liters. So 3.33 times 10 to the 5 liters of water. Are we expecting a big number? So the concentration of water, of chlorobenzene in this water is very low. But then we're trying to get 500 milligrams or 0.5 grams of chlorobenzene. And so, yeah, it's going to take quite a lot of water. We're expecting a big number rather than a little tiny number. Any questions? The thing about conversions and calculations with concentration units is that there's like almost an infinite number of ways that a question could be asked, right? And so we can't just learn a single formula and how to apply that. To do all of these problems, we have to be able to think about it and figure it out. 3.3 times 10 to the 4, that's not what I came up with. What went wrong? Let me try that again. 5EE2 times 1EE-3 times 1EE9 divided by 15. Well, I probably counted wrong. Yeah, I counted wrong. So instead of telling my calculator to put this in scientific notation, I counted and I counted wrong. That was a 7. And this is a 7, which makes this a 4. So 3 times 10 to the 4th liters. Mole fraction and mole percent are units that generally only chemists are concerned about. But mole fraction is this Greek letter chi. So the mole fraction of the solute is the expression, the concentration of moles per solute. I can't talk today. I'll start over. Mole fraction is the number of moles of solute per total number of moles of the solution. So for our solute, we're going to look at the amount of solute in moles divided by the amount of the moles of solute plus the moles of solvent. That's the mole fraction. If we take the mole fraction and multiply by 100, then we get the mole percent. A solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. So this is a lot of practice. So what do we have here? Well, we've got 50.4 grams of sucrose, we've got 0.332 kilograms of water, and we got solution volume. So I'm going to write those things up here because we're going to need all of that space. So I've got 50.4 grams of sucrose, which is table sugar. I've got 0.332 kilograms of water. I'm going to call that H2O. And I have 355 milliliters of solution. So the first one they ask for is the molarity. So then let's think about, well, what does molarity mean? Something divided by something. Moles per liter. So this is going to be moles of the solute, which is sucrose here, moles of solute divided by liters of the solution. Well, they didn't give us either of those. They gave us the mass of sucrose. Could we convert that to moles, though? Yeah, we could, because they gave us the formula. So we can calculate the molar mass. So 12 times 12.01 plus 22 times 1.008 plus 11 times 16. So that's a molar mass of 342.3 grams per mole. So if I take my grams of sucrose, I can convert that to moles of sucrose using the molar mass. And grams of sucrose cancel out. And as always, we want to be at least thinking about significant figures, even if we don't get them exactly right, giving it a good try, right? So this has 3 sig figs, and so my answer here should have 3 sig figs, but I don't want to round this yet because this isn't my final answer. So there's my 3rd sig fig, and then I'm just going to write down the 2 digits that follow it. If I carry 2 extra digits, I won't have rounding problems. So there's my moles of sucrose, right? So I can put this into the numerator, 0.14723 moles. And that's divided by the volume in liters. I was given milliliters. Well, we could use that little hack for converting 355. Instead of writing milli, I'm going to write what it means, times 10 to the minus 3 liters. Or you can set up a separate calculation and do it. That's fine too. It ends up being 0.355. So 0.14723 divided by 355 times 10 to the minus 3. And I'm going to get 0.41473, which I will round to 0.415 moles per liter, which is abbreviated capital M. Any questions? That's probably the most important of these units to be able to do stuff with. Okay, so next they want mole fraction. So what is the mole fraction? Again, it's something divided by something. It'll be the moles of the solute, so the moles of sucrose. This is like a percentage in that it's the part over the whole, but it's moles, not grams. So it's the moles of the part, which is moles of sucrose, divided by the total number of moles, which is kind of messy, but it's moles of sucrose, I'm going to call him suc, plus moles of water. Well, we have moles of sucrose right here. So I'll put that in the numerator, 0.14723 moles of suc. And then in the denominator, I have to take that number and add the moles of water. I don't have the moles of water. Let's create some space. What should I use to calculate the moles of water? The kilograms. So it said 0.332 kilograms. 0.332 kilograms, but when I'm doing molar mass calculations, we use grams, right? So instead of writing the little k, I'm going to write what it means. So 0.332 times 10 to the third grams. Or you can do that separately, or if you're good at moving the decimal point in the right direction, that works as well. So that's the mass of water, and then I'm going to use the molar mass of water to calculate the moles. It's just really not enough room on this slide. 3 sig figs, so 18.4. To 4 grams. Let's separate these guys. Did I do that right? Anybody following along? Calculator? I'll try it again. 0.332 EE3 divided by 18.02. Yep, that's what I get. Okay, so that's the moles of water, and it seems really big, doesn't it, compared to the other one? But this solution is mostly water, right? So the moles of water are going to be much bigger than the moles of sucrose. So then in here, I've got 18.424 moles. Yeah, I got the wrong unit up there, didn't I? This isn't grams. That fit better, but it's moles. So 0.14723 divided by the quantity 0.14723 plus 18.424. This is mixed division and adding. But most of the time, except for like on that, what was that, worksheet 2 or something? Most of the time, if we just look at the number of sig figs that we started with, we're going to be good enough. So we'll just go with that here. 0.0079279, and that would round to 0.00793. There is no unit on mole fraction because we have moles divided by moles, and so the units cancel out. Okay, molality, a really weird one. Well, what's molality? Moles per kilogram. So it's moles solute per kilogram solvent. So moles of sucrose per kilogram of solvent, which is water. Well, we already calculated the moles of the sucrose. So 0.14723 moles. And what do you know? They gave us the mass in kilograms of the water. How nice. So 0.14723 divided by 0.332. 0.44346, 0.443, and the unit there is moles per kilogram, or that funny little m, molal. The molarity of a solution and its molality are generally going to be very similar numbers. These are both 0.4 something, but they're not exactly the same. Okay, what's the mole percent? It's mole fraction times 100. So we already have the mole fraction. So this is our mole fraction. So we're going to just take that mole fraction and multiply by 100. Whoops. Any questions about that one? So the process here that we're doing is this is the unit they want, and we have to recognize, okay, what does that unit mean? And so we're mostly writing that down. And then we have to find the pieces and stick them in. What does percent by mass mean? Yeah, it'll be the part over the whole in mass, so grams of sucrose divided by grams of what? The solution, right? The whole solution. So by the grams of the solution and times 100. Well, they gave us the mass of sucrose, 50.4 grams of sucrose. What's the mass of the solution? There's two parts to the solution, right? The sucrose and the water. We have masses for both. So we need to add them together. But they need to be in the same unit. 0.332 kilograms that's going to be 332 grams of water. So here we've got the sugar mass plus the mass of the water. So 50.4 divided by the quantity, 50.4 plus 332 times 100. And this should be 3 sig figs would be a reasonable number here. So 13.2%. Any questions?
On the exam,
Mm-hmm.
we have to do like all of the parts like that, or
No.
just one?
No, I wouldn't ask you to do all of these as an exam problem. I'd ask you to do one, right? And then there might be another question about a different solution that's going to ask you for a different one. But yeah, I wouldn't make you do all of these. It's a little bit painful, isn't it? Do you know how many times I've done this particular problem? Way too many times. Any other questions? So the answers are out of order, aren't they? This 13.2 is actually the last one. Those percentages got switched. How is it that I'm only noticing that now? So this might be more like an exam question where you're just asking you to do one thing. What is the molarity of a 10.5% by mass glucose solution? The density of the solution is 1.03 grams per milliliter. So again, I think it's helpful to highlight the information that's given and highlight what we're trying to find. So it's 10.5% by mass glucose. What does 10.5% mean? 10.5 per 100, right? So that's 10.5 grams of the glucose per 100 grams of the whole thing. And that's not the only way to use percentages, but it's the method I've chosen for lecture just to be consistent, because I think it makes the most sense intuitively. Per cent refers to 100. A century is 100 things, right? 100 years. So it's 10.5 per 100. And then we're given the density is 1.03 grams per milliliter. That's the density of the solution, right? So that's the mass of the solution divided by the volume of the solution. When you're dealing with solutions, you have two different parts, at least. You have the solute and the solvent and the solution, right? I guess you have three things at minimum. And so when we have a mass or a volume here, we need to label what it is. Is this the solution we're talking about? Is it solute? Or is it just the solvent? So there we have our given information, and they're asking for the molarity. So molarity here, capital M, molarity is moles per liter, right? Moles of what? Per liter of what? Moles of glucose per liter of solution. So what we have been doing is we write down the stuff that we're given, and some of these look like conversion factors, and then we find the one that doesn't look like a conversion factor and we start with that one. This doesn't have one of those. Because what we're trying to find is also a per unit, moles of glucose per liter of solution. So this one can be a bit confusing for students. So we're trying to find the concentration in molarity. We're given the concentration in percent mass. So we're trying to convert this into that. And most students find just converting one unit into another enough of a challenge without trying to do 2 units at the same time inside of a fraction, right? So we can make this easier by saying, well, let's do these 2 conversions separately. We really don't need all that space in there. Oops. Let's bring this guy over here. Well, that didn't work out very well, did it? Let's do grams of glucose to moles of glucose. That is just, it's just horrible. So let's convert grams of glucose to moles of glucose, and then separately, let's convert grams of solution to liters of solution, and then we'll put them back together. Does that make sense? So I'm going to convert 10.5 grams of glucose to moles of glucose. You know, it's kind of a debate. Is it faster to write glucose or to write C6H12O6? I don't know. So grams per mole, we need the molar mass, right? I'm not going to write it out because we should be okay with molar masses by now. 6 times the mass of carbon, which is 12.01, plus 12 times the mass of hydrogen, 1.008, plus 6 times the mass of oxygen, which is 16, 180.2. Grams of glucose is equal to 1 mole of glucose. So 10.5 divided by 180.2, 0.0582. My starting number there had 3 sig figs. So even if I'm being sloppy with my sig figs, 3 would be a good number to keep. And that's going to be moles of glucose. So that's the top part here. 0.058268 moles. And now I want to convert the 100 grams of solution into liters. So 100 grams. Because the 100 here is part of the definition of percent, this 100 is an exact number. So 100 grams of solution, and I can use my density to convert that to milliliters of solution. And they said it was 1.03 grams per milliliter. But then I need this to be liters of solution. Milli stands for times 10 to the minus 3. So 1 milliliter is 1 times 10 to the minus 3 liters. So 100 divided by 1.03 times 1 times 10 to the minus 3. 0.097 0.87 liters. Here the number we started with had an infinite number of significant figures, but the density only had 3. So again, if you know by now if chemistry is your thing or not, and I'm guessing for most students chemistry is not their thing, and that's okay. And so sig figs might just be the least of your worries at this point in the semester, right? You've got bigger fish to fry. So as I mentioned before, generally if you use 3 or 4 sig figs in your answer, you're going to be safe, right? On the final exam, there will probably be at least one question that's asking you to pay close attention and figure out sig figs. But the rest of it, you just need to find an answer that's close enough to one of the multiple choice answers, right? So if sig figs are not your thing, just go with 3 or 4. Okay, 0.09708. Can't read my own writing. So now I'm going to do the math there. 0.058268 divided by 0.097087. 0.60016. 0.600 moles per liter. you might think, well, isn't there a faster, easier way to do that? If it's a conversion that you do all the time, yeah, you would come up with your own little formula based on all these things put together. But when you end up doing this to all different kinds of things, the best approach is to pick things apart, convert what you need to, and then put things back together at the end.